Greetings to all. We are group number 23 and our topic is Large Brain Model for Learning Generic Representations with Tremendous EEG Data in BCI. We'll be covering Introduction, Model Architecture, Experiments, Conclusion, Related Work, Pre-training Analysis and Visualization, Ablation and Masking and Embeddings, and References. Let's discuss and start by introduction, understanding what is EEG. EEG, electroencephalography. It records the spontaneous electrical brain activity. It is a non-invasive technique in which the electrodes are placed on the scalp using International 1020 system, and this is used in various applications like stress, sleep stages, motor imagery, and emotion recognition. Let's now discuss the current approaches in the EEG deep learning. The convolutional neural network based technique. In this, the CNN was applied across and within raw EEG channels and which encoded spatial and temporal features. This was done in paper like Lauren et al. In 2018. Second approach is spectrogram based GNNs, in which they pre-process the data using short time Fourier transform and then applied graph neural network on the resulting spectrograms, which gave them semantic features of the brain areas. This was done in Song et al. In 2018. Then there were segment-based CNN and RNN models, in which they use a CNN-based segment encoder with downstream sequence model like RNN to capture the temporal dynamics. For example, Zhu et al. In 2020. Let us now discuss what are the limitations of current EEG models. The task specificity and non-generalizable. The models are very specific towards the dataset and task as the equipments used to collect EEG differs. They have different channels and variable lengths. And there is also a problem of data scarcity, as EEG data is costly and difficult to collect. It is limited by its small sample size and short recording durations. Expert label data is also scarce and time intensive to generate. It has overfitting risk since small dataset force tight parameters controls, which prevents overfitting, and this limits the model's ability to generalize well. There is lack of unified representation learning, as EEG signals have low signal to noise ratios and very inconsistent formats. Existing models are using CNN, RNN and GNN based techniques, but they often struggle to balance the temporal and the spatial features. And therefore, many researchers are still relying on the handcrafted features. And there is no cross-task learning capabilities. They lack the flexibility for cross-task transfer or universal learning. Now let us discuss what is the motivation and inspiration from large language models. LLMs uses transformer architectures and mask token prediction. And it allows self-supervised pre-training enables general language understanding. And now let us understand, can the similar principles be applied to EEG signals? Now let us discuss how our model LabRAM works. What it does, it takes input EEG signals and which are splitted into fixed length patches so that varying electrode counts and time lengths could be managed. Now each path is passed through temporal encoder to extract the temporal features. Then the spatial and temporal embeddings are added to retain the context, and transformer encoder uses this patch-wise attention to learn the comprehensive representation, and then model is trained using masked patch prediction. Now let us discuss what makes this LabRAM unique. It uses the vector quantized neural spectrum prediction to create a neural tokenizer. It learns its new neural vocabulary from raw EEG patches using the Fourier spectrum prediction. It enables self-supervised pre-training similar to the masked language modeling, and it also handles EEG variability via flexible patch and embedding mechanisms. Moving forward, highlights. It has a large-scale EEG pre-training data which is over 2500 hours of EEG from 20 plus datasets, and it is the first of its kind in the BCI. Adaptability to different EEG setups. It works with EEG data of any channel count or time length. It has a robust EEG representations as it is able to learn both temporal and spatial patterns using token transformers, and introduces neural codebook for efficient EEG tokenizations. It has state-of-the-art performance. It is evaluated on 4 downstream tasks like classification and regression, and it outperforms all prior methods and scales effectively with more data. And now Sadhna will be discussing about the methodology. Thank you.
Hello all, I'm Sadhna, and now that we have understood what the project is about, let us understand the method. We'll be breaking this down into 3 parts: the model architecture, neural tokenizer training, and pre-training of the large brain model. Before moving on to the model architecture, let us first understand how EEG signals are represented. It is basically a matrix of size C by T, where C is the channels or the electrodes and T is the timestamps. Now, to handle inputs of variable lengths and process smaller batches easily, we segment these signals into samples, which is represented by the green vertical lines, and then for each channel, like each row is one channel. So for each channel in each sample, we segment it into patches. Over here, we see that the timestamp of each is T, small t, the stride is S, and the total number of samples is floor of T minus T by S plus 1. This looks familiar. We have used this to even calculate the output size when we learned about CNN. Now, each of our sample is of dimension C by small t. Once we've got our samples, we choose a window length W, and for each channel, we create patches of dimension W, where J is the channel index and K is the patch index. The total number of patches for one channel is T by W, and for C channels, it is C into T by W. This is per sample, right? Since we have the total number of samples, we get the overall patches as the number of samples that we have into the number of patches per sample. So this is the total number of patches for our signal. Now that we've understood this, let us move ahead with the model architecture. The model architecture has the temporal encoder, temporal and spatial embeddings, and transformer encoder. So EEG has high resolution in the temporal domain, and we need to extract its temporal features. So we pass the EEG patch to the temporal convolution blocks and get the patch embeddings represented as E, and where each vector is represented as ECIJK of dimension D, where J is the channel index and K is the patch index. The convolution block is one-dimensional and adapts group normalization and Gaussian error linear unit for nonlinearity. Now that we have the temporal embeddings, now that we have the patch embeddings, we add the temporal and spatial embeddings. This can be compared to how we add positional embeddings to word embeddings when we learned about how transformers process text. So the temporal and spatial embeddings are represented as TE and SE. Both are lists with elements of dimension D. Remember that the dimension has to be same as that of the patch embedding. TE, the number of elements is T max, which is a hyperparameter and has to be greater than the number of patches. And SE has the number of elements equal to the number of channels. Now, moving forward with the transformer encoder, the attention is similar to whatever we have learned from the lectures, just with a minor tweak. Instead of directly computing the dot product of the query and the key matrix, we apply layer normalization to both to ensure that the input is of a reasonable scale for the softmax, and then we scale it and take the softmax of it, multiply it with the value matrix to get the attention. Now that we've understood the model architecture, let us move ahead with the neural tokenizer training, which comprises of the neural tokenizer and the Fourier spectrum prediction. This is the neural tokenizer. Why are we trying to tokenize the signals? We are doing that so that we can work with discrete units. This can be compared to words in a vocabulary in NLP. Now we give the sample X, EEG sample X to the tokenizer, and we get the patch representation as discussed in the model architecture. Let us just hold on to the patch representation and discuss about the discrete codebook. The discrete codebook is a set of vectors of dimension k cross d which is used to represent the EEG patches. K is the number of neural embeddings and d is the dimensionality of each of these embeddings. So this is basically a lookup table for the patch representation, and we pass both of these to the quantizer, which calculates the minimum of the L2 distance of the patch representation and the neural embedding. And we get the quantized vector as the output, which is the closest neural embedding for this patch. L2 normalization prioritizes on cosine and direction similarity and improves the utilization of this codebook. Once we have the closest neural embeddings for each patch, we pass all of this to the neural decoder. The neural decoder predicts the amplitude and the phase of our signal. The loss used to train is the mean square error loss, and this is the equation of the loss. Let us go term by term. The first two terms represent the reconstruction loss, and the second two, the vector quantization loss. It is summed over all the patches for the entire data, and in the reconstruction loss, the first one is for the amplitude and the second one is for the phase. The vector quantization loss is basically the loss that we get from this step. And this SG means stop gradient. Stop gradient is applied to the patch embedding, which means that the gradient won't flow through this particular term. It will allow the other term to learn. So this term encourages the neural embedding to move closer to the patch embedding. And the fourth term encourages the patch embedding to commit to some particular code embedding. Now, we might question, why are we predicting the spectrum amplitude and phase instead of reconstructing the original signal? That is because EEG is has a low signal noise ratio, and it's really tough to reconstruct the original signal. So the solution proposed was to calculate the Fourier spectrum of the signal and then predict the amplitude and phase for this spectrum. To the left, we have the standard formulas for discrete Fourier transform, Euler's formula, and how to calculate the amplitude and phase given a complex number. And to the right is the implementation of these formulas. Given the EEG patch XCK for at a time point k and for a channel C, we calculate the spectrum for the sequence at frequency 2 by m by n as so. And using Euler's formula, we express this as a real and imaginary term. And then we reconstruct calculate the amplitude and phase as so. Now that we have understood this, let us go back to this slide and understand this term. Vector quantized means that we quantized the patch representation and found a mapping to a vector from the neural embedding. And once we have that vector, we have passed that and we are predicting for the Fourier spectrum, right? So from the neural embedding that we have, we are doing a spectrum prediction of the amplitude and phase. Now, moving to the last part, which is the pre-training, two things are done here. One is the masked EEG modeling and the symmetric masking. So in masked EEG modeling, this is used to learn the generic representations. So we have a sample X, which we give it to the temporal encoder. From the temporal encoder, we get the embeddings E. From E, we just pause on that, we generate a mask where 1 represents its masked and 0 represents that it's unmasked. Now when we overlay this, we get the masked or the corrupted patch embeddings as a union of the unmasked patches and the masked patches. Given this masked embedding, like before, we add the temporal and spatial embedding and give it to the transformer encoder, which gives us the output hidden vector. Once that is there, we linearly classify it to predict the corresponding neural token of the masked patches. And the objective training loss used here is the negative log likelihood of the predicted neural token given the masked patch. So this is the LM that is mentioned here in the overall pre-training loss. The second part is symmetric masking. We just generate the inverse of the mask we did here, and we perform the same steps as in masked EEG modeling with our inverse mask, and we get the symmetric loss. So this is the overall pre-training loss, which is the masked EEG modeling loss and the symmetric masked EEG modeling loss. Why are we doing symmetric masking? One, it improves the training efficiency because we're learning a more diverse masking perspective on the same data. And two, it reduces computational overhead since in the forward pass, it's done once per sample and it can be reused for the symmetric masking. So this is the summary of the entire model architecture. Let us quickly go through it. So this is the EEG signal that we have. We give it to the neural tokenizer. We get the patches. We calculate the L2 norm of the patch, and that we calculate the difference of the L2 norm of the patch with the L2 norm of the neural codebook. We find the minimum of this. We look and we find the quantized vector. We look it up from this codebook and replace the patch embeddings with the neural embeddings from the codebook. Once we have this, we give these neural embeddings to the neural decoder, and we predict the amplitude of the Fourier spectrum for our signal and the phase. To the bottom, we have the EEG signal. We generate the mask, and we generate the mask, and then we again tokenize it. We again tokenize it. We pass it to the temporal encoder, and then we add the temporal and spatial embeddings, and then give it to the transformer encoder, and then predict at these mask positions what is the corresponding token. Symmetric mask, as you can see, is just the mirror image of the mask, and it follows the same process, and we predict again the neural tokens at the mask positions. Now that we've understood this, I'll be handing it over to Aditya to now tell us how the model is actually running. Thank you.
So firstly we'll be looking into the experiments. The experimental results for LaBram, a new large brain model, which perform, and we'll be seeing on how it performs on the EEG data. So the key areas that we'll be looking into are pre-training dynamics, evaluation dataset. We'll also compare it to the SOTA. We look at the ablation studies, the scalability analysis, and as well as additional BCI tasks. Alright. Yes, the evaluation datasets. Firstly, it's the TOAP made by the Temple University Hospital, which has the binary classification of normal and abnormal EEGs. Alright. Moving on ahead, the TUEP dataset, which is again made by the Temple University Hospital. Unlike the TUAP, this has 6 different classes. Firstly, spike and sharp wave, generalized periodic epileptiform discharges, periodic lateralized epileptiform discharges, eye movements, as well as artifact and background. Both of them are 23 channelized, 256 Hz, and about 10 to 15 seconds of recording samples each. Alright. Now the team. Now there are 3 different variants made, namely base, large, and huge. Huge consisting of 369 million parameters. It was pre-trained on over 2,500 hours of diverse EEG data, keeping the evaluation data sets separate so that it does not hinder with the test or training data set, so it is not overfit. So the standard EEG pre-processing, like filtering and resampling, were applied. The LaBram was then compared to the current state-of-the-art methods using standard metrics for EEG analysis. So what did pre-training show us? Essentially, bigger models learned better during pre-processing, achieving lower loss and higher accuracy, as seen in the above figure. Also seen in the below figure, that the largest huge model kept improving as more pre-training data was added, showing it can really leverage large data sets. Right. So moving ahead, coming on to the SOTA comparison. Right. So how did Labram fare against the competition? On the TUAP dataset for abnormal EEG detection, Labram Huge achieved a new best AURC score of over 0.91. For more complex TUEV event classification task, Labram Huge also set a new benchmark with a Cohen kappa of around 0.6. Across the board, the larger Labram models performed much better. Alright. Moving ahead to the core components. Right. Uh, a key aspect in Labram's ability to generalize was seen in the figure. As seen in the figure, it shows that why the experiment learns universal EEG patterns and not the specifics of its pre-training data. The unsupervised pre-training phase itself is critical. Without it, the performance drops significantly. And features like spatial embeddings also proved essential for handling different EEG setups and capturing spatial info. So that was that. Let's look ahead to the broad applicability. Uh, also, Labram showed its worth on other BCI tasks. It achieved strong results in emotion recognition on seed V and gait prediction on mobile, with larger models again performing better. Encouragingly, for efficient adaptation, fine-tuning just the last few layers often yielded results comparable to retraining the whole model. So that was that. Moving ahead. Thank you.
Hello, I'm Taran. So to wrap everything up, here is the conclusion part of the video. So as we all know till now, Labram is a generalized model for EEG signals. It's kind of like a BERT for brain signals, but instead of text or images, it's trained on EEG data, and not just like little, but over 2,500 hours of brain recordings. So the thing that makes it special is it handles two of the biggest headache of EEG analysis. First is variable length of EEG data, and second is different number of channels across data sets. So how does it do this? Is like basically it uses a two-stage pre-training process. In stage one is like building an EEG vocabulary. First, it breaks the raw EEG into small patches, then each patch is turned into a vector using a temporal encoder. Then using vector quantization, it maps that patch to a discrete token, like turning brainwaves into words. The model then learns to predict the frequency content, that is amplitude and phase of the original patch from that token. Stage 2 is like learning the grammar of EEG signals. Once it knows how to tokenize EEG, it trains a transformer to predict missing tokens. Just like how LLMs learns language by guessing missing words. This teaches the model the spatial and temporal relationships of EEG signal, like how patterns evolve over time and interact across channels. And also they tested it on real world EEG tasks like detecting brain abnormalities, classifying different brain events, recognizing emotional states, predicting walking patterns from brain activity, and in every single task Labram outperformed the best model by the that time, the best models that exists. So here is some related work that shapes their approach. First, in self-supervised pre-training, there's been a huge progress in NLP and vision. Models like BERT and GPT changed how we learn representations from raw text by predicting masked or next tokens. In vision, models like MAE and BIT did something similar by hiding parts of images and training the models. These ideas gave them the confidence that masking based learning could even work for EEG2. Next, there's the issue of heterogeneous EEG dataset. As you know, the recording varies a lot, like different number of channels, inconsistent sampling rates, or different electrode layouts. Some recent solution tackled this head-on, like Triple M did tried to make easy representations independent of electrode configurations. And there's one research paper that used graph neural network combined with transfer learning to handle diverse setup. Also, some research papers trained models on both shared and full sets of channels, and others even used federated learning to let different dataset trains together without needing to be merged. These efforts helped shows it's possible to build flexible EEG models across varying data sources. Finally, a few work started exploring self-supervised learning in EEG and BCI directly. Like B and D are used contrastive learning to compress EEG signals inspired by wave-to-wake from speech, and one of them looked at temporal prediction and contrastive coding, whereas Contra WR used global stats to classify sleep stages. Brainbird tried masking modeling on spectrogram in SEEG signals, but the catch is all of these are focused on specific tasks and small datasets. None of them attempted large scale general purpose EEG pre-training like they do. So coming to Labram's pre-training analysis, this can be taught as an variational autoencoder but adapted for EEG data. The idea is to take an EEG signal, mask part of it, and train the model to recover its Fourier spectrum. We want to estimate how well we can reconstruct by giving masked input. This is done by maximizing the elbow on the log likelihood, which is represented by this equation. For simplicity, the token distribution is treated as a single point selection of most likely tokens. This simplifies our elbow to this equation. So in this equation there are two parts. The first part shows how to convert EEG patches into meaningful spectrum, and this second part shows how to reconstruct those tokens when part of signals are missing. So coming to hyperparameters, the table 1 shows the hyperparameters that are used for vector quantized neural spectrum prediction, and this table 2 shows hyperparameters for masked EEG pre-training, and the table 3 shows hyperparameters for downstream fine-tuning tasks.
Everyone, I am Aman Ban from MTech CSE. Today, I will be covering pre-training dataset description. Let me start by giving you a bird's eye view of a pre-training corpus for LabRAM spectrum predictor. Our purpose is that we assemble this data to teach our model how EEG spectra behave across a wide variety of tasks. Our scale was over 2500 hours of recording, so there is plenty of signal for the codebook to learn from. The data spans over 256 to 1000 hertz sampling rates and includes motor imagery, cognitive tasks, resting state sessions. These diversity is what lets our model generalize to new EEG patterns. Now next, let's drill into the standard benchmark datasets that forms the backbone of our training. Let's start from BCI competition 4 is to 1. There are 7 subjects performing left-right foot motor imagery at 1000 Hz, about 8.2 hours of total. There is another emo brain wherein 16 subjects in an emotion recognition task recorded at 1024 Hz for just under 5 hours. Grasp and lift. There are 12 subjects doing object grasp and lift trials at 500 Hz for about 11.7 hours. INRIA P300, covering over 26 subjects via P300 responses at 600 Hz, roughly of 30 hours. Motor movement imagery. It is a large data set of 109 subjects alternating baseline and imagery at 160 Hz for about 47 hours. Let's move into resting state and beyond. Starting from raw EEG data. In this over 34 hours of rule-based experiments, were followed by participants having precise instruction, producing clear, repeatable brain responses under controlled settings. Now, coming to resting state. It includes over 22 volunteers, wherein they alternated between eyes open and eyes closed, revealing the brain's natural idling rhythm without any external task. It was around 3 hours and was recorded under 256 hertz. Coming to seed series. Uh, these are the series which were subjects watched emotions, inciting videos, laughter, sadness, surprise. It was captured at high temporal resolution to show feelings sculpt EEG patterns. It was around 166.8 hours and was under 1000 hertz. Now coming to Cyana scalp. It is a real-world patient recordings which were introduced in artifacts and pathology-driven signals, ensuring robustness when data deviate from laboratory perfect condition. It was again of 30.5 hours under 512 hertz. What is the impact now? The impact of whole of this. This blend of controlled task, spontaneous rest, emotional dynamics, and clinical cases exposes the predictor to spectrum, follow spectrum of human EEG behavior. Now shifting to spectrum reconstruction insights. As we can see, there is a rapid amplitude loss reduction during the first 20 epochs. During the first 20 epochs, as we can see, amplitude error plunges as the code book identifies dominant spectral peaks, then settles into a consistent low plateau. Now, gradual phase loss improvement. Phase information emerges more subtly. Phase error declines steadily, reflecting progressive refinement of timing details. Near perfect amplitude reconstructions. Overlaying original and reconstructed amplitude spectra reveals almost complete overlap, evidence that discrete embeddings capture power distribution accurately. Sharpened phase reconstruction. The reconstruction in initial phase, the plots appear noisy. Uh, But later epochs produce smooth, faithful reconstruction of waveform timings. So, what are the key takeaways from this? As we can see, a compact, vectorized, quantized codebook can condense EEG spectra into discrete building blocks and then reconstruct both amplitude and phase with striking precision, bridging compression and fidelity.
Hello everyone, I am Rajiv Singh from MTech CSE. Now we will look at how the model perform on two additional brain related tasks. So first task is emotion recognition using EEG. In this task, a participant watched video and their brain signal were recorded, and the model predicted emotions like happy or sadness, and the dataset used in this task is seed 5. The goal is predict 5 emotion from EEG signals. The experiment collected EEG data from 20 subjects including 10 males and 10 females, and also the EEG signal are segmented into 1480801 second samples, and second one is gait prediction. In this task we are using mobile brain body imaging dataset, and this task is predicting how someone walk by reading their brain signal, and the model had to guess joint angle, which is more complex because it is regression problem, not a classification problem. And for result calculation, we are using metrics like Pearson correlation, R square, RMSE, root mean square error. And in result table we can see that when the data size is increases, the model accuracy improves in both task emotion recognition and gait predictions. Now move to the next vector quantized spectrum prediction. In this spectrum prediction, we set up three experimental. First one is predicting embedding, second one is reconstructing original EEG, and third one is reconstructing EEG spectrum. In predicting embedding, we directly predict output embedding of the neural tokenizer by maximizing cosine similarity instead of predicting the discrete neural token from the code book. In reconstructing original EEG, we discard the neural tokenizer and directly reconstruct raw EEG patches by minimizing mean square error loss. And in reconstructing EEG spectrum, we discard the neural tokenizer and reconstruct the Fourier spectrum of raw EEG patches by minimizing mean square error loss. And you can see that all accuracy in all three setup. Now move to the mask ratio experiment. And mask ratio experimented with how much of input signal to hide during training, and we tried different amount of signal masking from 10% to 50%, and we get that the best result is found at 50% mask ratio. And we saw that a model learn better when the half signal is hidden during training time. And in the in the performance of different mask ratio table, we see that accuracy on different mask ratio, and for 50% accuracy and for 50% masking accuracy is more better. And thank you.
So thank you Rajiv for explaining ablation on mask ratio. Now I will continue from here. Let's start from ablation studies. I'd like to start by talking about two things we tested under the hood, that is symmetric masking and spatial embeddings. In symmetric masking is like training random slices of our EEG signal and asking the model to fill in the blanks. It turns out that little puzzle game not only boosts our accuracy but also makes the prediction steadier, which is fantastic for real world reliability. On the other hand, when we remove the information about where each electrode sits on the scalp, the model struggles. This tells our approach really leans on the spatial context to make sense of the waveforms. Now moving on to the next slide. Now let's consider pre-training. We fed our network data from over 2,500 subjects during a self-supervised phase, and the difference is night and day. If you skip that, performance plummet by nearly 10 points in awk PR. In human terms, it's like learning a language without ever studying vocabulary. The sentence just doesn't make any sense. Finally, on this slide, the key insight is that one doesn't need to retrain the entire 12-layer transformer for every new EEG task. By freezing the first 8 blocks, which have already learned general EEG structure during large-scale pre-training, and only fine-tuning last 4 transformer block, the model retains over 95% of its full fine-tuning performance, while cutting compute requirements by around 60%. This make it possible to prototype sleep stage classifier or seizure detector in a fraction of the time and on much lighter hardware. That said, this strategy still depends on the access of large pre-trained model and at least a single GPU for tuning. And exceptionally specialized tasks may require unfreezing additional layers. Looking ahead, the plan is to introduce adapter and LoRa module so that even fewer parameter needs updating. Extend this recipe across diverse EEG paradigms, and ultimately fuse EEG embeddings with speech, text, or maybe imaging data, enabling brain-computer interfaces that understand not just your brain waves, but the context around them. So, thank you for your attention. On behalf of group number 23 from IIT Mandi, I hope we have made this paper clear and engaging. Thank you.